I always have to preface this by saying, I'm not a physician or even a clinical researcher. I'm an engineer, and so it's always a real pleasure to be invited to speak at this course to try to share some general insight that I think is relevant to clinicians and to clinical researchers we work with very closely. And it's not going to be any equations or anything in this talk. It's really more about guidance for clinical treatment, for clinical trial design. Okay, so I had to add some slides in the beginning because I was getting the impression I was boring Felipe a little bit with the same old stuff. So I wanted to add some fresh stuff. And this is this is data that literally was generated a week ago. But I think it does a nice job of introducing really what the question is. So I'll be talking about what this analysis is. This is analysis of dose guidelines, and you could see, for example, that's me without hair on top, right? These are MRI-derived images. To my left is a particularly obese individual who is part of a study here related to craving and things like that. To the right is another potential patient at Penn that may be treated for epilepsy. And so in all cases, you can see that the electrodes, the TDCS electrodes, have been placed on our subjects, right, simulated on our subjects. And a very basic question is, should TDCS be applied the same way in all these subjects, right? Should me, let's say I'm part of some sort of cognitive, verbal reasoning type, experiment, should I get a certain type of montage? What intensity should I be receiving? If you then want to, let's say, treat a kid, right, obviously investigationally, for autism, for epilepsy, should the intensity be the same, right, for the kid, right? We obviously there's a notion that with drugs you tailor the dose, right, both for the size of the patient, but definitely for the indication, right? One drug does not fit all. And same thing for the obese subject. The question is with so much fat on their head, right? And I'll show you later, there's a tremendous amount of fat. I mean, it's basically, it's not that their skull is bigger, right? It's just they have a lot more fat. And for the particular outcomes that they're looking for, should TDCS be applied the same way, right? Is it really one size fits all? Yeah.
I know you're into obese, for physical things. Is there any difference in any of the other experts in here can chime in? Do you find any difference in working with a thin versus obese patient in terms of cognitive changes? The brains are quite different in the obese versus thin person.
You mean baseline? Is their cognitive performance different, or will the TDCS?
Without stimulation. Regardless, with the stimulation.
I'll talk about that in one sense. What I'll be able to address is what these models will show you is how current flows through the brain in obese subjects, for example, versus normal subjects. So the models will address that. A secondary question is, will the way that their brains respond to the same amount of electricity, will that be the same or different? And I don't know the answer to that, but maybe I'll give you some hints.
Structurally, neurochemically, and electrically, the brains are different in a thin versus obese patient. This has been shown to be true.
Interesting.
And my question, again, is if anybody can answer it, does the thin person receive a higher level of efficacy with fewer or a shortened latency? You tell me.
So I would parse it into two parts. One is if you put this 1 milliamp, on me, and 1 milliamp, let's say, not that I'm the thinnest, right, but 1 milliamp on me and 1 milliamp on an obese subject, will the same amount of current reach our brains? Right. That's question number one. For example, in the obese person, will all the current simply shunt from one electrode to the other, never even entering the brain? So that's question number one, and I'll have some insight on that. Question number two is, assuming that the same amount, that the full 1 milliamp enters the brain in a healthy head, in an obese head, on a cellular level, will the obese head respond differently? And I don't know. That I don't know.
Does anybody know?
Whether the respond different or not.
In the fitter person, you're gonna have more BNF, BDNF, you're gonna have
Oh.
more interconnections, right? You're gonna have a denser, thicker brain compared to not as thick and dense brain in an obese person.
I think that's one thing you can think as well.
And cognitively, they'll be smarter. So would they be able to learn the new trait faster?
I think the only way you can think I see it is with some hormones as well. So if you could think that hormonal control is different, the neural endocrine axis would be different. So that might be one of the reasons we explain differences. But I'm sure that there might be differences in plasticity. No one has explored. I know that there's a difference in excitability, for instance, subjects fasting versus subjects after a meal. There are differences in excitability. So one of the issues you can even consider is that the difference because of that or not. It's still exploratory. No one knows well.
There's one other thing that might bear on it is with like sertraline, they did a trial with exercise versus sertraline depression, and there wasn't a statistical difference in the two. So the implication that the exercise improves response.
What year does that say? I know that Blumenthal 1999 does the same thing versus Zoloft.
Yeah.
Is that what you're talking about?
Yeah, sertraline is generic result.
Okay.
And then there's also, the cognitive improvement that if someone exercises, and then 3 hours after you get a cognitive.
I know of all this material. This is my expertise.
Yeah.
This is what I'm wondering if it leads, like, you knowing all this, does a fitter person, and knowing all this, should you exercise a person before you apply TDS?
You usually exercise after. I mean, that's the, it seems like everything's leaning toward you get the plasticity in the half hour, 45 minutes afterwards, that whatever effect happens, you can't. So since we know that exercise improves food, improves cognition, so if you do the TDCS and someone does aerobic exercise, then theoretically you get a magnification of cognitive ability.
So I think most of what I'll be talking about is really about that first question, about getting sort of the juice into the brain and how you might explore that differently, across these issues. But yeah, I mean, I think a lot of the cellular questions are much more difficult to get at. Another sort of, again, these were slides that, I mostly put together. I got to keep Felipe and Dylan interested. This is some additional simulations, and this is looking at different montages, right? So there's really a lot of flexibility. You may think of TDCS as a very simple technique, right? It's just like a stimulator with 2 wires and 2 electrodes coming out of it. But in reality, there's a lot of combinations, right? You can think about the size of the electrodes that we'll use. Does that matter? And also how many electrodes, and also where you position the electrodes. And when you start thinking about that, you realize that a single little TDCS box actually gives you an infinite number of possibilities as far as how you can customize it. And so the question is, should I be using again the same thing on everybody, regardless of the indication, or can I take advantage of this really simplistic? It's really easy to just put it somewhere else. How can I take advantage of that? And so this is again. I think this is going to keep happening. This is an example of that. So these are actually rather similar montages. In both cases, there's 2 smaller electrodes somewhere on the forehead and 1 return electrode. And so in the first 3, what's happening is that the position of these 2 small electrodes right here is being fixed. Let's say you put them over the prefrontal cortex, right? Or you're trying to activate frontal regions. And then you take the other electrode, the return electrode, and you just say, well, return means the one you want to ignore, right? And you put that somewhere else, right? Maybe you put that on the top of the head, maybe you put it on the back. In A, you can even see it's on the back of the neck, right? And what's immediately apparent is that where you put the return electrode affects what happens in the entire brain, including under the sort of electrodes of interest, right? So depending on where you position, can you see my mouse here? Yeah. So depending on where you position this return electrode, what happens in the prefrontal is completely different, right? So in this case, with the electrode in the back of the neck, it almost looks like the current is flowing down in this direction, and it passes through the brain right here, and you're affecting these almost lower regions. Well, in this configuration here, right, most of the activation is actually right at the top, right, the top of the head, because current is flowing from one electrode to the other, and it has to cross through these regions. And it is actually not in what you think was your region of interest. And again, I'm not explaining where exactly these pictures come from yet. I sort of just want to jump to the end. And here on the bottom, what's happening is that well, in the blue square, the return electrode is being kept at one place, and these electrodes are being moved. So starting from a higher location to a lower location, and here it's really just right over my nose. And once again, you can see that what happens in the frontal region, right, is completely different. The other thing you'll notice is here, under the return electrode, right, this is over occipital, you have a lot of activation. So with TDCS, you always have the anode, the positive terminal of the battery, and the negative, right, the negative terminal of the battery. And usually people will talk about anodal stimulation and cathodal stimulation, but you always have both. And when people talk about active, and they talk about return, the active is the one that they want you to think about, right, and to interpret their study based on, and the return simply means the one that they don't want you to think about. But the anode cathode can obviously be switched, and so a lot of times you may be running a study or a trial, and maybe the effects you're seeing are not, right, under your active electrode, especially if you're completely missing your target, but under your return. And so what I'm going to be showing you is how the kind of analysis, the pictures that I'm showing you here, how we generate what these pictures mean, why you should believe them or why you should doubt them, and then how you could use them. But I wanted to start off with some recent examples. This was with a group at Yale. All right, so there are different types of brain stimulation, right? We have the deep brain stimulation, we have the implants, the cyberonics, all those companies. These are invasive leads. We have the transcranial magnetic, and I'm sure most of you are familiar with it, or maybe even took the course. And then we have transcranial electrical. So just flying through this, the reason you drill holes in people's skulls, the reason is to be targeted, right? Why else would you drill a hole in someone's skull? It's complicated, right? So you're doing it because you want to implant an electrode near a target, and so it's really about focality. Transcranial magnetic stimulation, right? So you talk about transcranial electrical, that's a 9-volt battery. Transcranial magnetic stimulation, right? This is plugged into the wall. This is 1,000 volts, right? This is amps. This is, just from a cost perspective, right, 10 times more expensive, and you have potentially, if you do it wrong, right, seizure risks, right? Why? The reason they do transcranial magnetic stimulation is because it is perceived to be focal, or at least more focal than transcranial electrical stimulation. That's why, and it's also can be more comfortable in some cases, right? But one of the main reasons people use TMS, right, is the notion that the skull is transparent to magnetic stimulation. So when you put a coil over a brain region, you can actually specifically activate that brain region. Now, transcranial electrical stimulation, and I really mean low intensity here, right, the 9-volt battery type, not the ECT type. This has a lot of advantages as far as simplicity, tabletop. One day you could even imagine people taking it home, though certainly not today. But the main issue that it's not targeted, and I just showed you a few examples of that, right? If you put an electrode here and here, the current is going to flow through most of the brain, right? You're going to affect most of the brain, and so, and that is perceived to be, maybe disadvantageous. And so, I'll be coming back to that, but it sure would be nice, right, to have a focal transcranial electrical stimulation that keeps all the advantages, right? So like a small tabletop little stimulator with a 9-volt battery in it that gives you the best of all worlds, and I'll be coming back to that. But I do want to explain that the only difference between these technologies is how the electricity is delivered. In all cases, you're just getting the juice in the brain.